Hey, I'm live. That thing says I'm live. All right, antenna systems. We'll get into this. I'm just going to point out a few things. We got a long wire here and a long wire over here. This is the antenna from here to here. It could be this is also part of the antenna. It radiates. This is called ladder line, and I've got some examples I'll pass out here in a minute. So this is some sort of a dipole. We'll talk about these things, coming up, but just to explain the opening picture. So what does an antenna do? It transforms current into radio waves, transmits, and then it takes those radio waves and changes it back into current when it's receiving a signal. Feed line connects the station to the antenna, and then there's test and matching equipment that allows you to monitor and optimize the antenna system performance. So we're going to take a look at all of this. And again, as we move along here, I brought a small model of an antenna. If we just consider this part here, here's the feed line and whatever might connect to the radio at the opposite end. This is the feed point. Right here, where the center conductor is going to this element and the shield part is going to the top part. And we'll talk about these other two parts, other two elements a little bit later in a few slides. And this part of it can be called a dipole. Di meaning two, pole meaning long things. So there's two equal length poles here, hence the term dipole. So here's what we were seeing in that picture. There was a feed line, and unlike the picture was showing a lateral line. This is a coax. I'll show you the difference here in a minute. Coax has a center conductor. So here it splits off, it goes up to an insulator and connects to this side. The shield side breaks off and goes out here to this side. So again, we got a dipole here, two different poles going in an opposite direction. A good dipole is a quarter wavelength on each one. So altogether, this is a half wavelength long. Now, does it matter what frequency we're talking about, what band we're talking about? No, you can make a dipole for any band. And hence, it's not showing you frequencies here. We're talking wavelengths so that it's relative to what band you're talking about. This particular antenna is for 2 meters. Popular technician band to operate on. Well, whether you're a technician or any class, it's very popular. And a quarter wavelength. Then let me tell you this right now. It'll come up on a slide, but just to make it easier, remember that 2 meters, at 2 meters, again, it's popular, it's what your little radios are going to operate on. It's the washer repeater. It's in the 2 meter band. Quarter wavelength for 2 meters is a little bit more than 19 inches. And if you think about it, we call it the 2 meter band because a wavelength at that frequency, 144 to 148 megahertz, it's 2 meters long. 2 meters, we know, is a little bit more than 6 feet. There's 39 inches, so 3 feet, 3 inches to a meter. So 2 meters, that means 6 feet, 6 inches or so. A half of that, 6 feet, 6 inches, would be 3 feet, 3 inches. Half of that, I can do that math so well, but it comes down to about 19 inches. Well, let me just tell you, no, I can't do the math. It's up here in my head, it's 19 inches, or a little bit more than 19 inches. So that's quarter wavelength of 2 meters. That figure will come up in a test. And it'll be on the slide a little bit, but I'm emphasizing 19.2, 3, 4 inches, depending on where in the 2 meter band you are.
It's gonna be more.
Yeah, really. Everybody okay? Okay. Moving on here, some vocabulary. An element. The conducting part or parts of an antenna designed to radiate or receive radio waves. So these are elements. 1, 2, 3. Here's an element here. Here's an element here. Here's a little element. Elements. We're surrounded by elements. Look at the cars outside. Those antennas on all of the cars, whether it's receiving a satellite signal or amateur radios, those are elements. The driven element, this is the element that's not sure I understand that English. Anyway, power from the transmitter to the antenna, but it's also from the antenna to the radio is the driven element. So this center one right here is the driven element, or driven elements, not these. Are they up here? No. We'll talk about these. These are called parasitic elements. That'll come up in a minute. And an array. Array is an antenna with more than one element. So there is an antenna array right here. Not here, not here, not here, not there. Not on your cars. So here we've got a different type of this type of antenna. These are called these are directional antennas. They are also called Yagi antennas. Y-A-G-I. Yagi. I won't get into why we call them Yagis, or I'll save that story for another day, but we call these Yagis or directional antennas. They can also be called beam antennas. So there's the driven element, just like this one over here. This one has 2 directors up front. So the way this antenna is pointing is that way. I can't see it so well here. This is the long side. The long element, parasitic element, if such an antenna has one, is called a reflector. This is called a director. This is the driven element. So you've got driven elements here. You got reflectors here. It's the longest one. We won't get into the math of it, but what all of these elements combined together are doing. Did you get into wave studies in school in physics? You get a bunch of waves coming together from different angles. Some cancel out, some amplify the waves. And the way beam antennas operate, the principle behind them is the reflectors and the directors. Directors are kind of helping either receive or transmit out. The director is reflecting these things back towards the driven element on receiving or on transmitting. It hits that reflector and turns it around and reflects it out. And again, because there's distance there, that means one is traveling a little bit farther than the other one.
So they're not connected?
They are not connected.
Okay. Okay, so that's how they, so basically they're bringing to the middle.
Yes,
Okay.
and there is mathematics behind the distance. So different bands, different frequencies, as in this one, because things are pretty close together. This is a very high frequency antenna. This one's 2 meters, much lower than that one. So anyway, it's that combination of waves just slightly out of phase with each other that creates directivity and amplifies signals going into one area as opposed to the other. And we'll see that in a little bit more in a little bit. But I do want you to know this will be on the test, or possibly you got a reflector element, and it's a parasitic. The director is also parasitic. This driven element, that's very active, because here at the feed point is where the feed line connects to it. Okay, parasitic, the element's not connected directly to a feed line. Resonant, so an antenna is resonant when its feed point impedance has zero reactance. And again, at the technician level, we don't discuss or really get into reactance and capacitance quite as much as we will when we get to general, or if you go on up into extra. But this will be important when it comes to talking about standing wave ratios, which hopefully you're going to come up to. Feed point, this is where the transmitted energy enters the antenna, and the radiation, not radioactivity, an antenna emitting electronic waves. This is what radiation is doing here. It's radiating waves, not radioactivity. All right, so the thing about magnetic waves, radio waves are electromagnetic. So there's two parts of that, electric and magnetic. This is the way radio waves are physically built. The electric and the magnetic fields are at right angles to each other. So when it transmits, as it's going on over here in the diagram, you see the red wave is one way, and it's trying to depict that the blue wave is 90 degrees perpendicular to it. I don't think for the I don't think it matters at this point which is red in the electric, blue the magnetic, or vice versa. I don't know. All I know is they are perpendicular 90-degree angles to each other. They spread out in space from the antenna. They're created by AC current. And it's AC current because it's going up and down, cyclical, in such a fashion, just like coming out of the your 60-cycle box right there.
The imaginary box.
The imaginary box. Wave and current have the same frequency. So this is why, particularly at HF, where you're kicking out, usually the radios are putting out 100 watts. That can be really quite a bite if you were to touch that. Often, these little guys, they don't put out very much power, 5 watts or so. So if I touch the antenna, which actually is insulated, but if I were to touch the open center wire, I might get a little tingle. But on HF radios, that AC current can be quite high and give you quite a kick. Wave polarization. Orientation of a wave's electric field component with respect to the surface of the Earth, vertical or horizontal, determined by elements. Okay, so, and what this is assuming is we're talking about transmitted radio waves. The elements determine what way you're transmitting it. So if we go back to this guy over here, let's just say, for the sake of argument, the red is representing the electronic wave. The blue is the magnetic wave. The orientation then of this diagram is vertical. The orientation depends on the electric wave, not the magnetic wave. So in this particular case, this radio wave perhaps is being transmitted by this antenna or any of these antennas. These are all vertically oriented antennas. And usually, again, for the technicians, FM is almost always vertically oriented. So when you get your radios, whether little handy talkies, you put a radio in your car, whatever it is you're doing, if you're connecting it to a dual band radio, for example, 70 centimeter, 2 meters, your antenna is going to be vertical or near vertical. Like my antenna on my car, the trunk lid slants a little bit, so my antenna slants a little bit, and that's okay. But this is what we're talking about when we call it the polarization. And now let's move on though to, I think it comes up here. HF, when you're on sideband, when you're on Morse code, that is usually horizontal polarization. And in that case, I could make this a horizontal polarized antenna by bringing these things like this. Now I'm looking at that antenna, I'm still thinking, well, you know, those look like quarter wave antennas for 7 centimeters, but it's vertically operated. So what that's telling me is this is probably not going to be FM. This is somebody's operating sideband on 2 meters. That's an interesting place to be. So it's all vertical or horizontal. Now, circular, if the orientation twists as the wave spreads through space, and combinations of polarization are called elliptical polarizations. So that might come up on the test, but particularly vertical, how do we figure that out? Now, I'm going to demonstrate this. I have 2 field strength meters here. I got a real nice one here, Monarch. This is old. I picked this up from an amateur radio operator who was going to throw it away because he doesn't use it anymore. No, never throw amateur radio equipment away. It's always good.
Give it a carry.
Give it to carry. And I got another one here, also a field strength meter. This one was made in Japan. This one was made in China. I bought this one. I bought 3 of these because the price was holy smokes. They arrived and only one worked, the other 2 were junk. So here's my advice to you all. When it comes down to buying amateur radio equipment, don't buy the Chinese stuff. It's trash. Buy Japanese. Oh, I don't know. Buy Russian, maybe. But never buy Chinese stuff. I'm trying to keep my language clean. But for the purpose of what I'm going to try to do, sorry, I only got to. You're going to have to look over some of the shoulder or pass one off. Polarization is very important, that your transmitter and your receiver have the same polarization. And so I had 2 meters, you know, whether it's handy talking, whether it's a base station, whether it's a mobile, your antennas are usually oriented like this. Although with HTs, boy, isn't it cool? I'm just going to go around and talk like this because I'm a cool guy. All right, when I push my press to talk, I want you to watch, and do keep that straight up and down. I want you to watch that field strength meter. Let's see, maybe I get both of you guys. The field strength meter doesn't tell you how much power I'm putting out. It's only relative to where the signal is. So when I push this, here's MH2A testing. Are you getting any reading here? I'm too far away. Are you getting any reading? Okay, let me move a little bit closer. Are you getting anything? Okay, this is vertically oriented. Vertical here, vertical here. Watch what happens to the strength of the signal when I go horizontal. Do you see a drop?
No, it's an increase.
You see an increase, maybe because the antenna's going towards it.
Yeah.
Get back this way. See a difference?
Yes, now we do. Just a couple, just slight.
Oh, just slightly. Maybe if I go back a little bit further.
And this
Just
slight.
a little bit. Are you seeing anything there?
No.
You got full deflection almost? How about now?
0.
Zero. How about now? Full deflection?
Yep.
Okay. So what that's demonstrating is, if you go back to that diagram where it's all going up and down, the orientation is different. And so hence, it's attenuating when it's not oriented the same way. So when you go around timing on your cool handy times, don't be cool bag. If you really want your signal to get out, straight up and down or as straight as you can get it. Mobile antennas are pretty much oriented always straight up and down. Repeater antennas definitely are always straight up and down. So that's your best reception. You want your antennas to be oriented the same way. All right. Wave polarization. So here it is again. This could be a base station antenna or a repeater antenna, vertically oriented. Here's a great big long Yagi. Oh my gosh. Looks like the driven element might be right here. It's a single reflector, and then all kinds of directors going off in that direction. This big bad boy here, this is for satellite communication. Satellites, because they rotate, they use circular polarized antennas, and a circular polarized depiction would look something like this. Kind of confusing, depicting 3D spirals on a 2D surface, but that's pretty much what it would look like. Cross polarization. It is possible to have cross polarization, especially on HF. On VHF, UHF, as we just demonstrated, it's a little more, what would you call it, effective or ineffective if you're cross polarized. But by the time you get to HF, crossing those signals up a little bit isn't as bad. The attenuation is not as bad. And that's demonstrated by the fact that when those HF signals get up there into the ionosphere, they refract, reflect, they bounce, they backscatter, they get turned into all different types of orientation. And by the time it gets to the receiving antenna, some of it is horizontal, some of it is vertical, and a lot of it is in between. And you still receive and hear the signal. This is cross polarization, and it happens more in HF than it does in UHF, VHF. Otherwise, you won't hear it on UHF, VHF.
So if I understand optimally though, you want to have the same polarization in the antenna.
You do.
Same.
You do. So again, when you get into HF operations, It would normally be horizontally operated if you're using a dipole or a Yagi or a beam like this. But there are vertical antennas for HF, good old Cushcraft, which fired out some whatnot. Good vertical antennas. And vertical antennas in HF have a purpose. They've got qualities about them that are favorable. One, and again, I'm sorry, this gets into general. You're not going to need it for this, but vertical antennas usually have a lower takeoff angle. Verticals are much higher, and that's good because that means the angle of incidence here of the radio wave is going off towards the horizon. It reflects off the ionosphere over there, which reflects it down on the way over the horizon, as opposed to if I'm transmitting and shooting up in that area, it might come down and miss the Earth altogether type of a thing. So there are reasons for doing that. Cross-polarized antenna elements and the wave's electric field are at right angles. That can reduce reception by a factor of 100, and that was demonstrated here in what we just did. For elliptically polarized skywaves, such as HF, any antenna will respond at least partially. So not to worry about that. But VHF and above, you want to keep it as close to what the other antenna does as possible. The other thing here, I thought maybe it comes up. Okay, wait, let me go on further. I'm going to skip through all this because I've only got an hour left. So let me just, I'm going to read some of these just to make sure I'm not missing anything. Electric, these are at right angles. Defines its polarization. I did mention that. Orientation of the electric field, not the magnetic field. Two components, voltage and current, impedance and reactance, electric and magnetic field. So see. Okay, maybe we're not going. I want to pass this one out. These are different feed lines, all the different, and these aren't all of them. These are it's only a brief thing. But the coaxial antenna feed lines are these guys down here. Up here we've got what's called ladder line. Right below it, for the old guys. I don't see you guys here. TV line. The old, no, you're still the old TV line.
Thank you for thinking that.
300 ohms. So the rabbit ears would have been connected to this one. These are important. We're going to talk about that coming up here. Impedances. The top one is 450. The middle one, the 300 ohm twin lead is 300. And then all of these are 50 ohms. And we'll talk about why that is important as we move forward here. We'll also talk about line loss. Some of this is better than the others for different reasons, but because there are so many different purposes.
At our level, or I should say with hand rated stuff, you have to worry about line, like you have to put something in the antenna to compensate for line loss.
You could, or wouldn't be in the antenna. It would be at the radio and amplifier.
Okay.
But line loss is line loss, and it's going to be there no matter what you do.
Yeah.
So if I, instead of 100 watts putting into this antenna, if that line loss is going to be 50%, if I put 5 watts into it, it's going to kick out 2.5. If I put 100 watts into it, it's going to kick out 50. So the line loss is still there, but the more power.
So that's it. You just compensate for power.
Yeah. But the problem with that is the higher up in power you go, that power has to go someplace. And usually it's lost as heat. So the higher up you go, the hotter something is going to get. Now, how, if look back there, that one that's way off in the lower right corner, the RG316. Even though that's a Teflon outer coating, that still gets really, really hot. I can't put 1500 watts into that. I wouldn't advise it. But that thicker stuff up there, the RG400, I think, is the thickest we've got there. That will handle higher wattages, 600, RG600, and the Heliax, we'll get into Heliax here. That's really high. Handles that kind of heat better. All right, so some vocabulary here. Gain, you'll hear gain a lot. And sometimes some people either misuse it or they conflate it with other meanings of gain. So on a lot of the bigger radios, even bigger than this one, and it'll depend on manufacturer, what we call the volume, and we would expect to see on commercial radios, it'll be VOL. Some of these manufacturers of radios call it AF gain. And you'll look at that and go, where's the volume? I don't see the volume. Well, it's staring you in the face, but it's going by the words AF gain, which is going to be different than on also those fancier radios. You're going to see another one called RF gain. Completely different thing, has nothing to do with radios. Has a little bit more to do with your antennas, but it's not still even that.
AF.
Pardon me?
Sorry, AF stands for
Audio frequency.
audio frequency.
When we talk about antenna gain, we're talking about increasing or decreasing the radiated energy of that's coming out of the antenna. Isotropic. This is equal radiation in all directions. An isotropic antenna does not exist. It's an imaginary antenna. It's a single point in space that radiates equally in every single direction. And there is no such antenna as that, except up here in our imaginations. An omnidirectional direction is there's no preferred horizontal direction. That's this one, that's that one, that's that one. In a way, it's this one too, but this one is on its side. So these are omnidirectional in a donut shape in this direction, horizontal to the ground, even though it's a vertical antenna. Up here, the donut is this way. So this is radiating all around this way. The radio energy coming off this direction into the ground is wasted. Where going straight up is definitely wasted, because when it comes down here, it'll reflect. But when it goes up into the sky, it's wasted. That's why these vertical antennas are usually the best, because as your car is moving along, or you are moving along, as you twist and turn to talk into the repeater, doesn't matter which way you're traveling or walking, your antenna is still radiating equal energy in whatever direction you're twisting and turning around.
So it's going out distance, not just straight to the air.
Yeah. Up at this end, down at this end on these kind of antennas and this one, these are the null areas. Nothing or very little energy is going off in these directions, or in this case, off in that direction or back towards the wall. Not much going on. It's going this way. So you're getting some directivity out of it. And that's why this is called a directional antenna in particular, because all the radiation is coming. Again, I gotta figure out, it's shooting that way. Right into that picture. That's why everything is sinking over here. It's getting shot with RF energy. Okay, all right, so. How do I move forward? Okay, is that right? We're 10 minutes before 12?
It's
Yeah,
five
that
after
comes
11.
from-
5 after 11.
Oh,
It's
5
11
after
and
11.
5.
Okay, that's an hour off. Okay, so a little bit more depiction here. This is the isotropic, the imaginary antenna. No such thing.
So is it going, sorry, so it's going in one direction, right?
On the isotropic,
Well, I'm saying though, like for your antennas, right? You already said it, it's going in like clockwise direction, polarization.
yes.
Polarization causes it to go counterclockwise?
Well, it's not necessarily counterclockwise as much as it's radiating
Okay, so
in all
it's not-
directions
it's not going-
simultaneously.
Yeah.
So it's not moving, it's just a space that's
So
taken by,
when I'm talking about like that donut thing right here.
Yeah.
So what this is a, probably depicting a vertical, because it's only directional. Let's call it a vertical antenna. And when I key down, it sends out energy. As long as I've got the push to talk button pressed, it's transmitting RF energy. And so the donut is representing kind of the directivity and the power and everything that's going on while I'm pressing. The surface of this donut really is representing at that distance, if, it doesn't show a vertical antenna in the center of that hole, but it's there. So this surface of the donut is more or less representing what that energy looks like at that distance. I
so
could,
the space that it takes.
yeah, I could make that a much bigger donut and it is still representing the energy.
Okay.
It's further away, that law of inverse squares, it's a little less energy as I step away, and that's why when I push the top, wasn't picking it up very well if I was far away. But as I get closer, it might be like right here, this is where the edge of the donut is. Now, if we take a cross section, cut this donut in half, top to bottom, and look at it, it's going to look something like this. But again, it's at that distance from the antenna. But if we think about it, it doesn't necessarily, distance doesn't matter, as an absolute measurement. As a relative measurement, okay, because whether this is 3 inches or 3 feet from that antenna, that's still going to represent pretty much what the energy pattern looks like. I don't know what that wattage is. And the further out I go, again, inverse square law, it's less and less and less energy. But
So is this energy, is it moving?
yes, well, yes and
I mean,
no.
like, you know how a water goes down the drain?
Mhm.
Is this the same? Does it move like that? Or is it just?
Yeah, no, let's see if we can work with that analogy. So, as you watch, the swirling going on, and again, let's say I'm a transmitter,
Uh-huh.
and the transmitter is the water coming out of a faucet someplace that's creating that, if we're talking about that for the sake. Think of that as transmitter. The water itself is the RF energy. And as it swirls is kind of, I'll accept that too as perhaps what that energy is looking like. You must really want to talk to me here. So whether I am sticking my finger right here next to the drain, or whether I'm sticking it over here, the water's still going in that direction. Eventually down the drain. But as a relative strength and power, it's still there.
Right.
The energy is still there, it's still going in the same direction, but I'm just a little bit further out, so the current is not quite as much over here as it is right next to the drain. So I think from that perspective, it's moving, but
So this energy isn't like water, it's not going in one direction, it's just an energy that's there.
yeah, that's radiating out, yes.
Okay,
It's radiating out.
there's no, okay.
I don't want to give the impression though that that donut is moving. Or
Right,
anything.
the energy in it's not going in one direction, it's just
Think
radiating out.
that you have a sink full of water.
Yeah.
You drop a marble in the middle of it. You see ripples come out from that. That's exactly what that does.
Okay.
From that point, think of where the middle of that is where you drop that marble into the sink. All those ripples coming out in all the same direction evenly. That's exactly what that does.
Okay, I understand that, but the energy, so the
The
water.
ripples are the energy.
Okay, thank you.
Does that help?
Yeah, is it moving? No, so the transmitter is what's causing the ripple, right?
Exactly.
Okay,
The transmitter is when you drop that thing in the water, the energy coming out are the ripples.
okay,
That's-
so the energy is not a swirl pattern?
Nope,
It's just a
it
solid?
just radiates
Okay.
out in all directions.
Interesting, okay. That's crazy.
Did that help?
Yeah, it is
Simple.
I agree. I agree.
Wow.
Great, and they told me Navy training would never translate to
Because
anything
I
else.
asked him, because we were talking about directional, right? So it's like, so if in Australia, like, does it go a different direction? And then that's what swirl is.
Well, but also think about it like this too, and I like this analogy, and I'll put it into something a little bit different, but it's the same idea. If I have a small light bulb, I'll connect it to the battery, that light bulb is the transmitter. When I push the button to turn it on, it lights up. And so now that energy, that light energy is going in all directions around that bulb. Now, I can put my eyeball right up to it and burn my eyeballs because it's so bright. Or I can take a couple of steps back. It's still radiating in my direction,
But not strong.
but not as strong. Because it's still diffusing out. And that's kind of what this is showing. And now if we do something else, let's say in a flashlight, you've got that curved
Dome.
reflector dome.
Mhm.
If I put that over that light into the hole, so the light sticks up into that dome now takes all that light energy radiating out along the sides, but causes it to reflect. And now everything is going in that direction. Suddenly I've got a beam of light. And that's more or less what the reflector element is doing here. And these are helping it all. So this is why it's called a beam antenna, because it creates a beam of radio energy going off in that direction. In a flashlight, that's a reflector that is directing the light intensity. And then when I've got it like this, at any distance, well, I mean, it's bright light, but it's not so bad. But if I do that as a flashlight and now point it directly at me, oh, now I've got to step back even further because all of that light energy is now being directed in my direction. And now, so that goes a slide or two ahead of where I'm going with this, but what I'm describing there, that principle is exactly what it is with a beam antenna, a Yagi antenna, a directional antenna. It's redirecting. And Now that now gets to gain. This is what antenna gain is doing. It is redirecting all of that RF energy from what an isotropic antenna theoretically would do, or if we take it a step up, an omnidirectional antenna with this donut shape. Where I'm trying to think of another way to think of this. This imaginary isotropic antenna here. If I can think of it as, instead of a ball, or a ball of energy before it becomes a donut, which in an omnidirectional antenna, I think of that as a ball. Or if you will allow me, a balloon, a round balloon, not the long wiener balloons, but a round one.
Yeah.
If I poke my fingers top and bottom, that balloon kind of expands out a little bit, but the edges top and bottom get squeezed down, kind of like now we're in a funky looking balloon shape, but nevertheless, there's more pressure, more force going out to the edges. That now becomes representative of what an omnidirectional antenna is like. Is that making any sense?
Yep.
Okay.
Thank you, I heard that.
No, you're welcome. Yeah. And I appreciate your observation too. That well, this is interesting. This is, you never thought about it like this. And doggone it, you are right. I love antennas. I love studying antennas and making my own, as this one, and experimenting with it because I find it fascinating. So. I
When
agree
you
with
get
that.
to thinking about like airplanes and their antennas are like that, they're not like this. So that
Yes.
makes sense.
Well, and it depends. Okay, so I'm a pilot as well, and I can answer this one directly. Many plane antennas are kind of slanted back a little bit, but that's only for aerodynamics.
Oh,
Otherwise, they do want to be as straight up as they can. But what you might also notice on many airplanes and jets, the antennas are on top of the chassis or on top of the fuselage.
Mhm.
That's all right, but they can, and some aircraft have them on the bottom. Now, when it's down on the bottom, it has actually nothing in its way to attenuate, like kind of like with your question. Whereas when it's on top, it's a little bit harder. Again, this is a null at top and bottom. So if you're flying right over an ATC or a control tower, they may not be able to receive you if you're directly overhead. Now, if it's on the bottom, well, it's still in a null area, but now a lot of it's radiating, reflecting off of the bottom of the aircraft. They'll be able to hear you. Other aircraft, too, when they get up in long distances, international travel and whatnot, they switch to HF. And on older aircraft, they had a long wire from maybe just above the cockpit back to the top of the tail. And they directed their HF communication through that wire.
so is that why, like, when you're using cell phone stuff, there's too many ways to like cross over? That's why they want your cell phones off, so they have better communication.
Sometimes that's it, but I think back in the early days, FCC with FAA wanted to make sure that there's no crosstalk, no interference between your cell phone and the radio gear here for navigation. And a lot of that is being mitigated now with GPS. That's not as much of a concern as it was because old communications navigation systems were lower frequency and still are. Wow, I don't want to get into it because We're getting too far off track.
Sorry,
But,
sorry,
no,
sorry.
No, that's all right.
I'm the queen of that. It's not on purpose.
So, do you like trivia?
Yeah.
Yeah, well, I can tell. So, you know, we can talk offline, but that would have been one of the reasons, I think, is, so it doesn't interfere. But GPS is coming from a completely different area up here, although the newer stuff is now also being ground-based for greater accuracy, ADS-B, they call it. All right. So, isotropic antenna, it's an imaginary antenna that has no gain. It radiates in every single direction in free space. Does not exist. The omnidirectional antenna radiates it equally in every horizontal direction if it's vertically polarized. Otherwise, if you make it horizontally, now that radiated energy still there, still doing the exact same thing, but it's not necessarily horizontal. And I don't know what you would call this direction, but it's now always horizontal. Gain is expressed in decibels compared to a reference antenna. Now, we're not going to get into decibels. I've got to get into it a little bit. Decibels is used for comparisons. Decibels is it's a ratio of a device being measured or something that's being measured compared to a reference. And in this case with antennas, our reference is going to be either the isotropic antenna, imaginary, or and I is a good way to say this too. It's either imaginary or it's isotropic. Both start with an I. Otherwise, it will be compared to a dipole, a standard dipole antenna. So one is referred to as DBI, or one is referred to as DBD. They are not the same. DBI, you've got no gain, 0. So if I'm comparing any antenna like this to an isotropic antenna, the gain on this is always going to be better. And for a dipole antenna is always 2.15, I think.
Yeah.
2.15 decibels better than an isotropic imaginary antenna. And I'm going to show you something about that too. All right, so decibels, ratio expresses the power of 10 to make large numbers easier to work with. A decibel is 10 log for power ratios. It's 20 log for voltage ratios. Positive values in decibel indicate ratios greater than 1, and negative values of decibels are for ratios less than 1. Antenna gain is discussed in terms of decibels. All right, and again, I'm not going to get into explaining logs. You either got that in math in school, or you're going to have to study it when you get to be a general. As technicians, all you really need to worry about is this one, power ratio, log of 10. And we're going to show you some easy math here. And don't ask me why, because then we're going to get into the mathematics of it. And that's not the purpose of the class for our technicians. You don't need to know this. If you do know it, good for you. It'll come in real handy when you do general and extra. Doubling of power into an antenna. If that antenna has gain, like this one does, if I pump 5 watts into it, on a regular, on an isotropic antenna, that 5 watts is now divided in every single direction. So pick any direction, that is not 5 watts in that direction. That is 5 watts divided by 360 degrees this way, 360 degrees that way, every single direction. You've got a lot less than 5 watts in wherever you're standing around that antenna. With a Omnidirectional antenna, 5 watts is not, or any fraction thereof, is not coming out of the top, it's not coming out of the bottom, these are nulls. That energy is being redirected into this donut area around it. So while it might have been half a watt in any direction, it's now going to be maybe 3/4 of a watt because this wattage going up here and that wattage going down there needs to be redirected someplace. And so now it comes out here. Now I got gain. And this, how much gain depends on the design. If it's a dipole antenna, like just this center section, ignore the reflector and the director. Out of this driven element, this is a dipole. I can tell you it's 2.15 dB better than an isotropic antenna. Now, how much is that? I can tell you, see what?
Almost double.
Almost double. It's not 3 dB. I'm not going to do the math, but I can tell you 3 dB gain is double the power. And if I doubled that power again, okay, boy, let's see. 5 watts goes to 10 watts, goes to 20 watts. Okay, I got to do all that math. But if I just sit here and I think about it in terms of dB, there's 3 dB gain here. Okay. Now I got 6 dB gain. Oh, all right. I know I just doubled the double. I don't care how many watts we're talking about. Doesn't matter. And that's why when we do these kind of comparisons, doing it in decimals is a little more practical than doing it in actual figures. 100 watts, 1,000 watts, half a watt. Doesn't matter. I just know that 3 dB gain means I've just doubled the power. Or if I got minus 3 dB gain, I just cut it in half. Doesn't matter how much watts it is. So that's why doubling the power is 3 dB. Doubling the power and doubling it again, we add the two doubles together to 6 dB. So that's added. But if I'm thinking 5 to 10, now to 20, now I got to be doing some math, especially if I'm talking about, 3.5 watts. 3.5 watts, add that. Okay, now, but 3 dB gain, double that, 6 dB gain, easy. I'm done. Increasing power from 50 to 100, that's 3 dB. Cutting 30 watts to 15 watts, that's a 3 dB loss. 10 watts to 20, that's 3 dB. Increasing that 20 to 40, 3 plus 3 is 6 dB. All right, this is a lot to go over in the last 30 minutes. Now let's look at one more, 10 dB. 3 dB is going to be important to remember. 10 dB is one more to remember. 10 dB is increasing power by a factor of 10. So if I'm going from 10 watts to 100 watts, that's 10 dB gain. 14 watts increasing to 140 watts, that's 10 dB. Decreasing power, minus 10 dB. 1,500 watts decreasing to 150 watts is a minus 10 dB gain. And it works the same way if I were to take 150 watts and decrease it by 10, again, down to 15 watts, that's minus 10 plus minus 10, that's minus 20 dB loss. Here's a chart, ignore this column, because we're talking voltage here, and technician, we do not worry about voltage. we're only talking over here. 0, 3, and 10. Those are the only ones you need to know. Doubling the power or increasing power by a factor of 10, or doing the opposite. I put this is a package to a Diamond handheld antenna. Almost every antenna manufacturer is going to tell you what the decibel gain is. It's up to you, the consumer. Are we talking about DBI or DBD? Now, they got DBI gain of 2.15 decibels compared to imaginary or isotropic antenna. Yeah, you know what? That's, what's a polite way to say this? That's a bunch of baloney. This is a marketing trick. In other words, this antenna is no better on 70 centimeters than an imaginary isotropic antenna. Well, no, I take that back. It's no better than a dipole antenna. 2.15 is how much better a dipole antenna is over an isotropic antenna. So what they're trying to tell me, this is a pretty slick antenna, but it really isn't. Radiation patterns. We wanted to talk a little bit about radiation patterns. That's where before we were taking that donut and cutting it in half. Although if that was the omnidirectional antenna, that was almost the perfect circle. This is a funky little thing here. This is a directional antenna. The back side of the directional antenna, which was this side here, is not radiating very much energy at all. So this is the null side of a directional antenna. All of the energy is coming forward and off to the sides, over here and over there. Little less energy directly next to it. This graph is calibrated in decibels because we have no idea, any amount of energy can be coming through that antenna. So instead of sitting here and putting watts on it, we do this in decibel comparisons. I might say if the more elements you've got, the more directivity it's got, the sharper that thing begins to scope down. I think we'll see one of those in a minute. Nulls, direction of minimum gain. This side. Lobes, these are the regions between null areas where there's energy going out, but not here. There's a null area, or maybe over here is a null area. Side lobes, lobe other than the main lobe going forward. Forward gain in the direction the side is forward. And we took a look at it from the side, but you can also be looking at it from the top. And when you're looking at it that way, now you'll see those angles of incidence, all the different ones. And so like a vertical antenna I mentioned before for HF, lower takeoff angles, so these lobes will be looking like that, a butterfly, wing spread. A horizontally oriented dipole antenna, those lobes are going to be a little bit higher up. And so here's what we're looking at. These are the main lobes. Here's a side lobe, because this is pointing straight up. So this is the side. A lot of energy is being wasted by going straight up. But the main lobe's over here. This is what we're most interested in. So these may change. But when you're looking at it um, from the side, you're seeing the directivity going off in one particular direction. This is a good thing. Here's one with many different types of lobes. This is for a directional antenna. There's something called the front-to-back ratio. A little bit of energy usually escapes out the back. A lot of energy going forward. So that ratio is what's the amount of energy coming out of the back to the amount of energy going forward. And then the front-to-side ratio, there's a little bit of energy coming off the sides as well, maybe a little bit more than the backside. But you can also do that as a ratio of forward gain to the right angles of the forward direction. So that's this one right here. All right, let me just do one or two antenna gain. Just remember that's an increase in signal strength in a specified direction compared to a reference antenna, either dipole or isotropic. So here, this is the kind of stuff you're going to get on the test. There may be, well, there'll be at least one question that's going to talk about decibels. What's power increase from 5 watts to 10 watts? What are we doing here? Doubling the power, doubling that antenna gain. And that's going to be how many decibels? 3. That's a 3 decibel gain. Here, decimal value represents a power decrease from 12 watts to 3 watts. Well, now this one I maybe do need to think about a little bit, but I do know 12 divided by 2, if I'm having it as 6, I have 6, I make it 3. So 3 decibel loss and another 3 decibel loss. I add the decibels. So minus 3 plus minus 3 is minus 6. And this one, you might get this one. This is we're talking 10 decibels here because we're talking in powers of 10. 20 watts to 200, positive 10 dB. All right, so that's the first half. Do you mind if we not take a break, or does anybody need to take a break? 'Cause I'll see how far we can get in the second half. Okay, feedlots, practical antennas. See how quickly we can zip through this one. All right, so this touches on something I've already gone over. These are different types of feed lines. Open wire line, also called ladder line or window line. That was this one up here. Coaxial, co meaning together, axial meaning an axis. So any wire that's got another wire right in the center of it is coaxial. And there were lots of coaxials on the table there. Power is always lost as heat in the feed line. This is called loss, and it increases with frequency. The higher I go in frequency, the more loss there is going to be. Doesn't matter which one of these coaxials or ladder line you use, the higher up in frequency you go, the more loss there's going to be. And when we get the microwave towers and cell phones and stuff like that, you can literally see the wires on the side of the tower going up. Those are really thick coaxial lines that allow you to see it from whatever distance you are from the tower, that you can see it, as opposed to when you go by a ham radio operator in his tower, I see the tower, I see the antenna, and I don't see the coax, because he's using that kind of coax. Open wire, so know that the twin lead is 300 ohm, know that the lateral line is 450 ohms. That might come up on the test. Flexing, whether it's open wire line or anything else, will over time cause it to break. Yeah, some other things here. Lighter, less expensive than coax. Has lower loss than coax at most frequencies. More difficult to use since it's affected by nearby material. This is insulation from the center, or insulation from the conductors. So hopefully if you touch it, you're not going to get shocked by it, unless you're doing the bare wire. But it's not RF insulation. It's radiating. So if you send a radio signal down this line, radio lateral line or twin lead, it's radiating. Coax has a braided shield, and that keeps the radiation within the shield on the center conductor. That requires impedance matching equipment to use it with most receivers, most modern day receivers. And when I say modern day, I'm going to say anywhere from the late 40s, early 50s to right now today. Most modern receivers are transmitters, transceivers, let's call it. 50 ohms, it wants us to get 50 ohm impedance on that line. And these coax for amateur radio is 50 ohms. So because this is 450, this is 300, that's a mismatch. That's going to cause problems unless we've got some matching equipment to help make the radio think that that's 50 ohms instead of 450 or 300. That's why we've got down here higher impedance may complicate the use. Okay, coax, most common feed line. Easy to use. It's not affected by material nearby because this is the braided shield, outer shield. This is the center conductor that's really carrying the RF energy. It has a higher loss than most open line at most frequencies. So that's not a good thing. And then there is something air insulated, hard line we call it, has the lowest loss. The hard line, let's see if there's a picture of it coming up. Okay, there will be a picture coming up if we get to it before in the next 17 minutes. Air insulated is called hard line because it's really thick. It's very difficult to bend. The center conductor is surrounded by air, and there might be a heliaxical insulator going through the center of it, but most of that is air inside there. Air is an insulator. But that's called insulated hardline. It's also called heliax from the helical interior. Multi-strand center conductor. If you took a look at this, or you want to take a look at it again, the RX-8, the RX-8X, the LMR 240 here in the these three, maybe these down here too, and this one. These are multi-strand in on the center conductor. This 240 and this LMR 400 is solid. Nope, I take that back. I see 240 is also multi-strand. LMR is the only solid strand antenna or coax strand. If it's solid core, it's harder to bend. It'll bend, but it's not as flexible as multi-stranded inner coax. So just a little bit here, the center conductor, the dielectric, that's the insulator on the inside. The outer conductor, usually it's braided, and then you've got the outer insulator, the outer insulation. That kind of protects the whole thing. Larger diameter coax have lower loss. Loss is also measured in dB per 100 feet. I'll get to that in half a minute. Now this one says dB per foot, but sometimes it's more efficient to compare everything to dB loss per 100 feet. Loss increases with frequency. The higher you go in frequency, the more loss, doesn't matter which cable it is. With coax is susceptible to getting water in it, and if it does, you've got ruined coax. Usually, coax will leak in two areas. The shielding itself will crack, and it will crack as it gets older with age and exposure to sunlight, UV rays. It will also get moisture depending on the connector. One connector type is better than some of the other connector types, and we'll get to that in a minute. Some coaxial cable is UV rated. It'll be more expensive. And coax is getting pretty darn expensive as it is right now. Here's the hard line I was talking about. Here's the helical insulation. It helps keep that center conductor evenly distanced from the outer shield. Very difficult to bend. This one's got foam dielectric in it, but this one, air dielectric, lowest loss. So if you get that question, what's the lowest loss? Look for air insulated dielectric. Common coaxes, here's a whole bunch, but I want you to concentrate on RG58. That's thin stuff. Trying to think. RG58 and RG8X. This one's 8X. So you can see this one's kind of thick, but look how tight I can bend that. That's great. This guy here is thicker. I can't bend it as tight. This is LMR 400. That could also be not 8X, but just RG8. All of that is 50 ohm impedance. Most coax characteristic impedance is 50 ohms. 75 ohms. So RG58 is the most common used in amateur radio, along with LMR 400 type. There is not RG58, but RG59. Your cable companies use RG59. 75 ohms. Boy, when they go through and they replace your underground cable, as they've done at my house, it's like, oh, they're just leaving that, 400 feet of RG59 in the ground, because it's easier, more efficient for them to just dig new stuff. It's like, I'm gonna go rip that out, which means I gotta go through my yard, pulling that all up. But now what do I want to do with it? It's not going to work very well with my amateur radio equipment without some proper matching devices in there to make the radio think it's 50 ohm instead of 75 ohm. Here is a chart of some coax comparisons. dB per 100 feet. Here's RG58. Down here we're at 3.2. So by the time if I'm going to use this on 50 hertz, 50 megahertz, that's the 6 meter band, I have lost half of my power at 100 feet. And if I'm going to use it up in the microwaves, oh boy, that's a big, big loss. Here I'm almost, well, let's take a look at 440. We're very close to 10 decibels. That's a 10 factor loss. So if I'm sending 100 watts to my 440 antenna, only 10 watts is getting there. Now, and you'll notice here, the higher in frequency we go, the bigger the loss. You'll notice that for it doesn't matter which one of these examples, the higher you go, the more the loss. But as we're going out this way, we're getting thicker and thicker. LM400 is this little guy right here, and it's on that sheet, wherever it is. So, you know, almost a 10 factor loss here at 440, but it's only 2.7. It's not even 3. And I know 3 means half the wattage is getting there. LMR 400 is really good if you're going to be going up that high. But LMR 400 is a hell of a lot more expensive than this guy. Connectors. A couple of connectors here. The important ones to know are the SO, well, actually, I would say PL259. I wish I had a connector chart like that coax chart. Here's a weird device. Doesn't matter what the device is. I can tell you that that's a PL259 connector. That is used quite commonly in amateur radio. They call that a UHF connector. But it's really good only up to VHF. So use this on your 2 meter. Use this on anything below 2 meters, any of your HF radios. But if you're going to go up to 70 centimeters or above, your connector you want to use then is an N connector, N like Nancy. I'll pass this one around. This is an elbow connector, but both connectors are N males. N males and PL259 connectors are not interchangeable. PL259 connectors are waterproof. PO259, water can seep into the connector itself, or it can seep into the coax. Bad thing. So if you're going to do PL259 on anything, wrap your coax around the connection very well. And we'll talk about that in the next one. So UHF connector is also PL259, but it doesn't work very well at UHF frequencies. Why do they do that? I don't know. There is a reason. I do know the reason, but I'm not going to go into it because I've got 8 minutes. N connectors is for UHF and above. A lot of stuff use SMA connectors. SMA are what are on most of today's smaller radios. If you were to unscrew that, one of these is a BNC connector on the red radio. BNC is which Carol. This is the same on both ends. Here's BNC connectors. F is for cable TVs. You won't see those. PL259, N connector, BNC connector, SMA connectors. Just remember, N is for best used on UHF, 440 and above. PL259, also called the UHF connector, but it's terrible on UHF. A little bit about there's three major ways to connect connectors to coax. Solder them on, crimp them on, compress them on. A lot of ham radio operators are liking the compression connectors. I haven't gotten into those. I've spent too much money for crimping equipment to crimp my connectors. Crimping is better than soldering. See the art of soldering on the AARL website. Obtain or borrow crimping tools. Like I said, I've spent a lot of money on crimping. Anybody who wants to crimp, I encourage it. Find someone like me. I've spent the money on crimping tools. I hardly ever use it. Come and borrow my crimping tools. Don't spend $300 for your own crimping stuff. Waterproofing. So you've got to waterproof everything. Use good quality electrical tape first. Wrap it around the edges. Then a layer of self-vulcanizing tape. So that's kind of like electric tape. It's pretty stretchy. It stretches, and as you stretch and twirl it around, it now starts to contract back on itself. But when it's touching other vulcanized tape, it fuses together. And that really does a great job of keeping water out. And then if you wrap regular vinyl electric tape around that, that makes a really solid waterproof connection. Air core coaxial cable, if you ever get into that, this means you're going to be working with repeaters and microwave stuff. If you ever get around to that, those connectors require a special type of connectors and special techniques to waterproof it. Okay, I'm going to skip on one of this. Sorry. Five minutes. I'll just touch on this. We're not talking too much about doing your own soldering, but there will be a question, there could be a question on solder joints. A good solder joint is going to be shiny. It's kind of going to be in a bit of a, I don't know what you call this, a pyramid or a cone shape. Very nice, but the big thing is it's a shiny finish. A dull finish. It's got the cone shape, but it's very definitely very dull, pitted. Sometimes it's got crack around it, a cracked ring. That's a bad solder connection. So if you can remember that, shiny is good, dull is not good when it comes to soldering. All right, you've heard me talk about 75 ohm and 50 ohms, but I didn't really explain it. It's given in ohms. It depends on how the feed line is constructed, what the material is used, and all that. We're not concerned about it. All I know is when I buy the coax, I want to make sure it's 50 ohms. And if it's any of those LMR 400, RG58, RG8, RG8X, doesn't matter. I know they get their names because of That's how the coax was built to those specifications. It's going to be 50 ohms. Standing wave ratio, this is also very important. The standing wave ratio, hard to see down here, but if the transmitter is over here on the left, the green wave represents the RF energy that's going to the antenna over here. If it is not a good 50 ohm match between the antenna and the feed line, or the feed line and the radio, there's going to be a loss of energy. If that's a perfect match, 50 ohms over here at the transmitter, 50 ohm coax, 50 ohms over here at the feed point, all of the energy is going to transfer to the antenna, and the antenna will radiate it. If not, in this case, the red is showing that there is not a perfect match here. Some of that energy goes out through the antenna. The rest of that energy is either shot back towards the transmitter and it's lost as heat. Your line will start to heat up, or that feed point, either at the antenna or at the radio, begins to heat up. That's a bad thing. Modern radios will begin to shut down to protect itself. If it detects energy coming back, then it's going to say, oh, don't put out that 100 watts. I'm only going to put out 50 watts because I'm detecting too much energy coming back at me. So I need to protect myself. I'm reducing the energy I'm putting out. Standing wave ratios is a ratio. It's measured 1.0 to 1. That dot 1, the 1 is always at the end. It's the number in front. This is the important one. 1.0 to 1, that's a perfect match. There's never a negative number in an SWR field. 2 to 1, well, I'm okay with a 2 to 1 SWR. But if it goes above 2 to 1, if it's 3 to 1, 4 to 1, 5 to 1 or higher, look, this is really bad. I am not going to transmit with that. There are instruments, the one field strength meter had an SWR meter in it, the other one did not. Modern radios, like the one in the red over there, has an SWR meter built into it. I can show you afterwards here, if you stick around, what that antenna currently is. It's not a very good antenna. None of these antennas that come on HT are very good. SWR is usually pretty high on HT antennas. Nothing is perfect. SWR above 3.0 is considered very high. High SWR can be corrected by tuning the antenna. You can't see it so well here, but some elements, my German element, I cut it too short. You can't see it so well, but I have taken this much from another rod and soldered it to make it longer. Know that if I need to make an antenna, the longer I make it, the lower the resonant frequencies go. If I need to tune it to a higher frequency, I need to start clipping things. Trust me, it is better if you're making your own antenna. It is better to make an antenna too long than too short. So if you're making your own antennas, make them long, easy to snip, 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 snip and test, snip and test, snip and test. Because if you make them too short, it's a pain in the butt to have to go out there and solder stuff like this onto it. Doesn't look very pretty. You don't want to show your friends. It's too embarrassing. Impedance matching equipment at the transmitter is called an antenna tuner or a transmit. Antenna tuner is an incorrect term. It is not tuning your antenna. Your antenna is still untuned. It is just compensating and fooling your radio into thinking it's transmitting into a 50 ohm feed line. But that mismatch is still there. There's still going to be heat transfer, which means it doesn't change the SWR in the feed line. All right. The rest of this, you're going to have to look in your books because I'm now 2 or 3 minutes past the time. I'm sorry about that, but here's what some SWR meters look like. One is showing the power output and what the SWR is. It looks like it's 2.8 over here being transmitted right now at a power of, it's down here is on 200. So we're doing 10, 20, a little more than 30 watts out. This one over here, this shows both happening at the same time. The power going forward and the power coming back. And then these drawings in the middle here show you the SWR. You got to interpret it. And in this case, 2's here, 3's here, so this looks like it's about SWR of 2.5 to 1. Acceptable. Here's what it looks like on a radio, the modern ones. Let's see. It's on the SWR meter. Here it's on the power. And here the SWR is less than, that's 1.5. This is close to 1.1 to 1, 1.2 to 1. That's great. So it's putting out, here's on the power. That's the scale right here. 20, 30, 40, 50. So about 28 watts is going out. So the radio is kicking out 28 watts, but because it's a low SWR, it's probably a true reading. Okay. More examples on bigger radios. Antenna analyzers. Here, I use this one quite a lot. This shows me where the resonant frequency is and whether I need to make my antenna bigger or smaller. I really like Rig Expert. It's made in Ukraine. It hasn't been bombed yet. We're always looking for the lowest SWR. We usually will find a U shape like that. That's a great curve. This is telling me my resonant frequency is around 146 point something, to maybe. So I want to tune my antenna there. Okay, I think that's going to have to do it. See, we're not even getting into the antenna stuff. Okay, until next week. Next week we'll do, what are we doing next week?
Chapter,
Radio equipment, chapter 5.
yeah, would it be okay to continue the rest of this and then?
That's gonna really slide in everything.